AP Chemistry, this is a continuation of the Day 64 answers video, and we're now on problem 7. So let's go ahead and read this. It's a combination reaction or synthesis reaction producing nitric oxide from nitrogen and oxygen gas. So this is still going to be a concentrations problem. It could have been a pressure problem, but it's a concentrations problem. It can be that for a gas as well. So you have 0.5 moles of N2 gas is mixed with 0.86 moles of O2 gas in a 2-liter tank at 2000 K. So the way that sentence reads, those are initial numbers of moles, but they're not concentrations, they're moles. Concentrations are moles per liter. So they tell you how big the tank is, so you're going to have to do a little bit of a division problem there to calculate the number of liters. All right, and again, the temperature just is saying that it's at some fixed temperature that that the equilibrium constant will apply to. Okay, what are the equilibrium concentrations of each substance? So there's the equilibrium constant, the Kc, at that particular temperature. And anyway, there's the answers that you have to check with. So let's go ahead and write the reaction out. All right, so we need to do a little math to figure out the molarity. So for N2, it's moles per liter. That's molarity. That's what concentration means. So that's going to be 0.5 over 2 liters. And that's going to equal 0.25 molar. So that's the initial concentration for N2. For O2, and O2 it says it's 0.86. Okay, so that initial concentration is 0.43. All right, and since they don't give us an initial concentration, let's go ahead and write our arrow there, because that's our product over there. Since they don't give us an initial concentration, we assume it's 0. All right, so now we write in, and you're going to get to where you can just write these almost just by looking at it. Think about whether you can do that now. You know this is going to be a minus x, because you're starting with this, and you don't have any of this, so the reaction can only go in one direction at this point, and that's to the right. The coefficient in front of the N2 is a 1. In front of the O2 is also a 1. So this is going to be minus x. And this has a coefficient of 2, so it's plus 2x. And now you just create your algebra equations down there. Okay, so now you have your algebra equations to put into the law of mass action, so create the law of mass action. Okay, now that I've completed the Rice table, I'm going to go ahead and do this on a separate piece of paper because I see I'm going to need more space than what I had down there. Again, if you're doing this on line paper, that's not an issue. You got all the space you need, but it's probably going to take a little more space. Okay, so we're going to go ahead and write the Rice table for this. So it's going to be product on top, and the coefficient becomes the exponent, and then reactants on the bottom, coefficients are both 1, so you don't need to write anything for the exponent. Okay, let's go ahead now and let's plug in these values. Plus, we know what the K equilibrium equals for this reaction at the temperature that it's being conducted. So let's go ahead and do that. So it's going to be on top is 2x squared. That should actually be 2x in parentheses and then squared. Down on the bottom for n2 we have this. Okay, so that's the reaction. And then we know what K is. We know what K equilibrium is. It's 4.1 times 10 to the minus 4. And I ran off my page. Okay, so there it is right there. 4.1 times 10 to the minus 4, this number right here. Okay, so now we got this problem to solve. It's going to be a big mess because you got an x times an x, that's an x squared. You're talking about a quadratic. On the bottom, you can see clearly from what you remember from math, I hope, that that's going to be an x squared plus something x plus a constant, and it's going to be a mess. So this is where we're going to use the simplifying assumption. If this number is very, very, very small compared to this, then you can just ignore it. For example, if this number, I'm just making up a number, if this number were 0.00001, then 0.25 minus 0.00001 would basically just be 0.25. It's like you're subtracting nothing from it. So what we're going to do is we're going to eliminate these. And so now all we have left is that times that, 0.25 times 0.43. So I'm going to move over here. I'll just rewrite it. Again, remember, don't forget to put those parentheses. It's 2x is the concentration right here, and that goes in, that represents that, and then you have to square the 2x, not just the x squared part of it. It's not just 2x squared, it's going to become 4x squared. Okay. Alright, so let's start simplifying this. I'm going to multiply this and that on the top. So that becomes 4x squared on the top. You square the 2 and you square the x. On the bottom we have 0.1075. That's these two numbers multiplied together. And that's going to equal. That's going to equal this. Okay, I'll just continue my calculation over here. So I'm going to multiply both sides by this. It's a bad place to draw that arrow. Not get good planning there. So these cancel. Alright, so we have 4x squared equals, and we're just going to multiply the 4.1 times that. And that gives us this. Now we're going to divide both sides by 4. It's all just math at this point, which for some of you might be the toughest part. So we have x squared, and this divided by 4. Okay, now to solve for x, we take the square root of both sides. It's always a little tricky to take an exponent, the square root of an exponent. That's always a little bit tricky. So let's just do it on the calculator. Okay, so here's calculator. So this is our number, 0.11 times 10 to the minus 4. So we're going to do a second and x squared. That gives us the square root. 0.11 times 10 exponent hat caret negative, not minus sign, but negative, not this minus sign, this one, negative 4, and then close the parenthesis. And it doesn't, sometimes it'll give you the answer on this calculator in scientific notation. In this case it didn't. So it's 3.32 times 10 to the minus 3. Okay. Okay, well, we're getting down here on the page a little bit. Well, that's all good. Let's come back up here. I'm going to partition my paper there and write this up here. X equals 3.32. So that by itself is not our answer. What we need to do is go back to our rice table, and we need to plug this into each of these. Okay, so we still have more math to do to get this. So even though we didn't have to do a quadratic, we still have a lot of math to do. So let me move this down here. And I'm going to start with the easy one, 2x. So it's going to be 2 times so this will be 6.64 times 10 to the minus third. That's going to be the concentration of NO. Okay, and if we check our answers up above, I'm going to move this so you can see it. That's what we got right there. Okay, so that one checks off. Okay, we got the next two to do. So this is for, let's write what it is. It's for NO. It's the concentration of NO. It's the equilibrium concentration of NO. So be sure you can explain in words what that number means. And since it's a concentration, it should be in molar. Okay, so that's the complete answer right there for the concentration of NO. All right, let's keep going here. So where are we? So the next one for O2, I'll write that over here since I did NO over there. Okay, so that's going to be 0.43, and it's going to be minus this. It's a little weird to subtract, but a calculator can do it. That's where a calculator will come in. Minus 3.32 times 10 to the minus 3. Okay, so again, that's if you had to do that in scientific notation, you'd have to convert this to where it's an exponent of 10 to the minus 3. So this is 4.3 times 10 to the minus 1. What you'd have to do is change that to 430 times 10 to the minus 3. Anyway, I don't want to go there. You can just do it on the calculator. Let me get on screen here. So now that you see what we're doing, that we're plugging the 3.32 times 10 to the minus 3 in for that x. So 4.43 minus that, so that's what we have here. So we'll go ahead and do that on the calculator. Let's see what that looks like. Come back here, 0.43 minus parenthesis 3.32 times 10 caret negative 3 minus 3, close parenthesis, and we get 0.43, just call it 0.43 is probably good enough. Okay, so the concentration of O2 equals 0.43. There's no exponents, there's no scientific, it just gave us the number. So look what you saw. You saw that x was so small that 0.43 minus x is 0.43. That's what we're talking about, that x being so small that it doesn't affect it. Now when you're multiplying, you can't do that. You can't just say that 2 times this, forget about this. But when you're adding or subtracting, you can say forget about this. Okay, see what happens? So this equals that. So this number was so small that you could have just neglected it. That's why we X'd it out up there, okay? There it is right there, 0.43, and what we X'd out there, and there we do. You got that, okay? So I know I'm kind of beating this point to death, but I want to be sure you understand why you're doing that and why you can do that, okay? Let's see, and our answer up here, O2 is 0.427, that's fine. 4.43, same thing. Okay, one more to do. And that is N2. So we want the concentration of N2. And it's going to be 0.25 minus that really, really tiny number. So I'll bet your answer is going to be 0.25 there, isn't it? So 0.25 minus 3.32 times 10 to the minus third. Okay. Again, that. So again, where we got that from is right there, 0.25 minus what our value of X was, which is 3.32 times 10 to the minus third. So we're going to do that on the calculator. Okay, 0.25 minus, parenthesis, 3.32 times 10 to the negative third, close the parenthesis, and you get, I get something wrong. Let's try it again. Let me clear it. 0.25 minus 3.32 times 10. Oh, I forgot to put my caret in. I didn't reach up there. Okay. Negative third. And hit that. And there you see it's pretty close to 0.25. If you rounded, it's 0.25 to 2 decimal places there. Okay, so the concentration of N2 equals 0. And I'm just going to round it to 25. Okay, still not done. You got to prove that your assumption was justified. So we come back here, and we could use either of these initial concentrations, but let's use the smaller one, because if our 5% rule is going to fail, it's going to fail by putting the X over the smaller of the two numbers. That's going to be the least significant, least important difference there. Okay, I don't want to use the word significant, but the least wide difference, okay, is going to be between this and the small number. So let's go ahead and do that. So I'm just going to write 5% rule, and that's going to be 3.32 Okay, so just do this and then move the decimal over 2 places. So I'm doing 3.32 times 10 caret negative 3 divided by 0.25, and that gives, and then I'm going to multiply that by 100, and I get that equals 1.3%. So that's less than 5%. So we're okay. We were okay to make that simplifying assumption and just ignore that value of X, okay? As I say, that's always going to be the case, but I want you to prove it each time just so I know you're not saying, oh, well, it always works. It doesn't always work, but it is in these problems generally, okay? All right, so that takes care of that. So you see, this is a lot of writing, so you got to keep yourself organized in these problems, okay? There's just a lot of math to write out there, as you can see. It's just math. It's just math you've all had. So, again, keep that organized. All right, so that was 7. It was everything. Let me show my camera. Everything you see here and all the way down there. Okay, that's a full page to do that problem. Okay, let's move on to 8. And again, I'll get it started here. I may move to another piece of paper. We'll see how much space we need to do that. All right, Number 8, equilibrium constant for this reaction. Okay, so they're giving you K. We'll call it C. It could be Ke if you want. Again, they're giving you a temperature just to state the temperature's not going to change. If the initial concentration of hydrogen, and that should be iodine, are both 0.25 molar, what is the equilibrium concentration of HI? Okay, so there's your reaction. So go ahead in the reaction, go ahead and write it. You've seen this reaction a lot before. And as you're going to learn in the next lesson, this is hydroiodic acid. It's a strong acid. Okay, there that is. Now the initial, they give us initial concentrations. And there it is, 0.25 for both. Okay, and they say, what's the equilibrium concentration of HI? All right, so if they don't give you an initial concentration of HI, you assume it's 0. That's always true. That's never considered suspect to do that. That's the way these problems are done. Okay, I didn't finish writing that. Okay, all right, so let's go ahead. See if you can fill this out. I'll bet you some of you by now can actually write the law of mass action in terms of the algebraic expressions. You could probably do that right now without even, you've done it actually for this, but not with these numbers exactly. But go ahead, do that. Okay, pause. You can always pause, you can always go back. Okay, so I'm going to move forward. So these coefficients are 1. So this is going to be minus 1x. Okay, and this is a 2. So yeah, we have seen this before. So 0 plus 2x is 2x. 0.25 minus 1x. Same thing here. The fact that those are the same is going to make this an easier problem mathematically. You'll see that coming up. Okay, so there's in algebraic form what your equilibrium concentrations are. Now go ahead and write the law of mass action. First write the general form of it. What I mean is use these up here before you plug in numbers. Okay, now you can plug in your algebraic expressions here. And you can plug in your Kc as well at 60.2. Okay, and what we can do, I said this is going to make it easier mathematically. It's going to be 0.25 minus 1 times 0.25 minus 1. So we're going to just write that. I'll get rid of the 1. I think we're done with that. And you can just write that as a square. So you have a square over a square now. So that makes the math easier. Okay? Okay, so now we're solving for x. So what we're going to do is I'm going to move up here where I have some space. I'm going to take the square root of both sides. Since I have a perfect square over a perfect square, okay, I can only do that if these two were the same. So that just simplifies the problem a little bit. Okay, and then we're going to take the square root of this side, so that's going to look like this. It all goes under the square root. Okay, and I'll move down here. I'll go take the square root of 60, figure out what that is. And I get 7.76. And on this side, I simply get the 2x squared square root is just going to be 2x. So the square root erases that square. Same thing on the bottom. The square root erases that square, so it's simply this. Okay, at this point, do you eliminate that? Well, you can. It's not saving you from a quadratic, though. So I'm going to go ahead and keep it there. If you don't really have to save yourself from doing a quadratic, keep it there. So I am going to this. I'm going to go ahead and multiply. I have the space here. Let me partition this so you can see what I'm doing here. Get rid of this arrow. I don't really need it. Okay. So I'm going to multiply both sides by this. They cancel. Okay. So now I just distribute this 776 times 0.25. And again, I'm going to go to another piece of paper. You want to take my lead on that because, you know, not enough space there. Okay. So I'm going to bring this over here. So 7.76. Again, it's just math now at this point. It's not chemistry. And that's 1.94. That's this times 0.25. Minus 7.76 times x. Again, we'll test it at the end and see if we could have gotten rid of that x, but let's not assume we always can, okay? And then on this side, I have 2x. Okay? So I multiplied this both sides. I canceled there. 0.25 minus x, 7.76 times 0.25 is that. 7.76 times negative x is that. And the 2x stays over on the right. So I'm going to add 7.76 to both sides. 7.76x to both sides. That goes away. And I have 1.94 equals 9.76x. Divide both sides by this. I'm off screen, I'm sorry. Okay, so what I did was I added 7.76x to both sides. This one canceled. That becomes 9.76x. And then you still have the 1.94. Now we're going to divide by 9.76. We need to solve for x. It goes away. So that means x is going to equal, I'll put the x over on the left. And you're going to divide 1.94 by 9.76. Boom. And I get 0.198. And I'm tempted to call that just 0.199. I'm going to call it 0.2. I'm going to take a chance and say that we can round it to that. And I'll put a 0 there. Okay. All right. So that's the value of x. So now we come down here and we're going to plug that into 2x here. I tell you what, I'm not going to do that. I tell you why, because I peeked at the answer up there, and it looks like I didn't do that when I did this the last time. So I'm going to put that 199. Okay, 199. All right, so we see right here that the concentration of HI is 2x. So concentration of HI from our ice table equals 2x, which equals 2 times 0.199, which equals 0.398 molar. It is a concentration, so it's molar. Okay, so there it is for the concentration of HI. Come back here. Concentrations of H2 and I2 are going to be the same. So we'll do that. 0.250 minus 1x, so it's just minus x, so it's just minus this. And that's going to give us 0.051. It's too late. I can't do it in my head. Sometimes I can't even do simple calculations. Yeah. Okay, so that's it. And that's molar. That's the concentrations of either of those. So let's test and see if we could have used the 5% rule. There's X. Could we have just eliminated it back here when we had that? So doesn't look like it, does it? Okay. Your initial concentration's of 0.25 and X is 0.199, so let's just see what that is. You get on screen. Okay, so it's whatever your X value is over the initial concentration. You can do it for all initial concentrations. In this case, it's the same for both H2 and I2. And then you're going to multiply that by 100%. And let's see what that gives us. Oh my gosh. 79.6%. That's way over the 5% rule, okay? So you can't eliminate the X. Back when we had the chance to do it, you can't do it. Okay? You could not eliminate it right there to simplify. It is not much smaller than that. It's almost as big as that number. That's a pretty big X, okay? So again, don't assume that you can do it. Generally, you know, the little tip-off is if you're gonna end up with a quadratic, then yeah, you'll probably get rid of that X. They're probably giving you one where you can get rid of the X, okay? All right, so again, we got a lot of stuff here. So let's look at the camera, look at all that, okay? Not quite as long as the last one, but these problems can take some space. But it's all math. The chemistry is done up here, and then the rest is just crunching the numbers and getting the math. Okay, let's keep going. We're doing good. All right. If I2 has an initial pressure of 1 atmosphere, what are the equilibrium pressures of I2 and I for the reaction? Okay, so this reaction just has one reactant, one product. Let's write them in. It's just an iodine molecule being decomposed into 2 iodine atoms. You have a Kp for pressure, and we're dealing in pressure. Okay, so we don't need this. We don't have enough reactants or products to need that. Okay, so initial. So I2 has an initial pressure of 1. So let's just put a 1 there. Okay, and it doesn't tell you for I2, so you can put a 0. Okay, this is going to be minus 1x. Okay. So that's going to give you 1 minus x. I'll just leave off that coefficient 1. And this is going to be plus 2x because of that. So this is going to be 2x. This looks like an easy problem, algebra problem. I hope it is. Hope we don't need 3 pieces of paper for this one. Okay, here we go. So, law of mass action, it is a gas, but that doesn't matter if everything's done the same. So it's I, concentration of I, squared over I, concentration of I2. Okay, so this one is going to be 2x, and then you've got to square that. And this one over here is going to be 1 minus x. You don't have to square that or do anything to that. And that's going to equal the KP, which they gave you as 2.91. Okay. Oh, wait, well, this still can end up as a quadratic, can't it? Huh, look at that. Okay, so what's going to happen here? Well, we're going to end up, I'm going to bring it down here, we're going to end up with 4x squared. That's this. Okay, and I'm going to multiply both sides by 1 minus x, so that means this one's going to go away and it's going to end up over here, okay? I hope that wasn't too tricky in algebra. Well, let me just write it, 1 minus x. There, cancel, cancel. And there it ends up over there. All right, so let's do this. So we got 4x squared. Okay. Equals 2.91 times 1 is 2.91 times 10 to the negative fourth. And then it's going to be that times negative x. X. Well, since this is going to end up with a quadratic, right, we're going to have to move this over here and this over here so that this whole big thing equals 0. Then you have a quadratic. Then you got to plug all this ugly scientific notation. I'm betting we can just eliminate the x. We could have done it right here, but I'm going to go ahead and do it right here, right there. Say that goes away. Now we have a much simpler problem. And again, we're going to test it at the end to see if the 5% rule, to see if this x value is less than 5% of 1. So that means it would have to be 0.05 or less. Anyway, let's just go ahead and do it. We're going to divide both sides by 4. That cancels. So you have x squared equals 2.91 divided by 4. And that gives us 0.738, 0.728. Times 10 to the minus 4. Remember, this whole adjust the decimal in scientific notation, that only has to do with the final answer. You don't have to do that in the middle of the problem. You just go ahead and work the problem with the number you have and deal with the, adjusting decimals, moving it over and all that stuff at the end. Okay, so I'm going to take the square root of x squared. Okay, there it is. So this is simply going to be x. Again, I am going to go down to another piece of paper. Let me move down here. Okay, so this becomes x. And this, we got to do this on a calculator. So let's see how we do that again. Second, and then x squared is going to be a square root. And then you just type that number in exactly the way you see it. 0.728 times 10 caret minus 4. Close the parenthesis and hit equal. And we get 0.00853. And in scientific notation, that's 8.53 times 10 to the negative third. See, it's a little tricky doing exponent square roots. It's not half of this or twice this or anything. It's a little tricky. Okay, so there's our x. So what's the question asking for? I forgot. They want the equilibrium pressures of both of those. So for I2, move this up here. The equilibrium pressure is going to be 1 minus x, and there's our x right there. Which equals equals 0.991. Okay, and that again is a concentration, so it's molar. Okay, you can see that number is very close to 1. So this number was really tiny compared to that. So we'll still do the 5% test, but we're probably going to pass our test there, okay? Okay, this one is 2 times x, and that's for I. It's not for 2I. I mean, that's part of what you use the calculation. It's for the concentration of I, just iodine atoms. Okay, and that's going to be 2 times this number. So that's going to give us 17.06. Okay, now since this is a final answer, it's the molar concentration of this, you have to adjust the decimal. So you have to make a number between 1 and 10, so we're going to slide it over to there. 1.706. We made this number smaller. We went from 17.06 to 1.706, so we made this number smaller, so we have to make the exponent bigger. And bigger than -3 is going in the positive direction, so that's -2, and that's molar. All right. Okay. All right, so let's test it. Let's see if our X, the only concentration we have to start with, it's always with the initial concentration. And technically you should test all of them if there's more than one and they're different, but in this case we just have one. Okay, so we're going to do this. So we're going to come down here, we're going to do the 5% rule test. We're going to take X over initial concentration was 1, that's really easy, times 100%. So it's just going to be this times 100 and then put a percent sign on the end of it. And what we get is 0.853%. So it's less than 1%. So it easily was less than 5%. It has to be less than this. Okay? We want to show that that eliminating X was a valid assumption. And we did that right here. We just kicked it out of there. Otherwise, we would have had to solve a quadratic equation with all this because of that x squared and that x and that constant there. Okay, so there you go. Did I give you answers on this one? Yeah, 0.991 and yeah, that's, I wrote it in scientific notation. That's it. That's 1.71 times 10 to the minus 2. That's what we got there. That's close. 1.7. Okay. All right. Good. Let's keep going. I hope these are starting to feel familiar now. You'll see it's the same 5 steps. The only thing that makes them seem, kind of messy is there's a lot of math, a lot of number crunching. But I hope the concept of how you do these is making sense and that you could explain in words what are you doing. Okay, you're finding what are these concentrations where this reaction finds its happy place and just kind of stops, and how much of the product how much of the reactant is it going to have at that point when it stops reacting, and how much of the product is it going to have. And that's what this is all about. So chemists need to know this stuff for a whole lot of reasons, but your reason for wanting to know is because of the AP exam. Okay, so now we're going on. I think we got one more, and then we got some Le Chatelier principle, and those are fairly quick and easy. Okay, let's do this. Where am I on time? I'm at 51 minutes. I'm going to go over, I'm going to break. I want to get this up, so I want to give you a chance to do this. So here we go. I'm going to post this. I'll do the last 2 problems and the Le Chatelier, because I might want to spend a little time talking about Le Chatelier's principle. It's kind of an important, it's not numeric, it's just a concept, and I want to talk about that. Okay, so I'll see you on the next video.